in physics, the laws of conservation are very, very important, and they give us powerful tools to be able to solve problems. Just like we learned in the previous chapter about the conservation of energy, right? So here we learn about conservation of momentum. So first let's learn what momentum is, and we'll define a few other things such as impulse, which is related to momentum. So momentum, we write it with the lowercase letter p. It's a vector quantity, right? So it has this arrow above it, it's in bold. And the magnitude of the momentum is given by the mass times velocity of an object. So if a very massive object, like a big truck, is speeding down, it has a higher momentum compared to a much smaller, let's say, car, which is speeding with the same velocity, okay? So the more massive an object is, and the greater the velocity is, the more momentum it carries, the harder it is to bring to a stop, yeah? So P equals m times v. M is a scalar quantity, v is a vector quantity. This is a vector equation, which also implies that your momentum is going to be in the same direction as the velocity, yeah? We saw this kind of equation earlier in F equals m into a, where the two directions for force and acceleration were always the same, they matched. Similarly for momentum here. Since mass is a scalar quantity, all it does is change the magnitude of that vector, v, right? But it doesn't change the direction, since mass can never be negative, so it's always in the same direction exactly. The units for momentum, you can simply multiply the units for these two. So mass is in kilograms, velocity in meters per second. So kg meters per second is the unit here. Okay. Like any vector quantity, if we're dealing with two dimensions, say x and y, we're going to split the momentum into its components. The x component of momentum given by mass times velocity x, the x component of velocity, py equals mass times y component of velocity. And this is a useful formula to know kinetic energy of the object. Remember, it's associated with motion, so that's 1/2 mv squared equals p squared divided by 2m. And it's quite simple to try to prove this. So you should try to do that on your own, and I'm going to show you here. So instead of p, we can write m into v whole squared, so mass squared times velocity squared divided by 2m, right? So I've just written exactly this over here, just broken down the p into its constituent two parts, mass times velocity. Now we can algebraically cut these two. And what does that leave you with? That leaves you with 1/2 mv squared, right? Which is the same as kinetic energy. So sometimes when you're doing a problem, it's helpful to be able to know immediately the connection between kinetic energy and momentum, okay? So you need to know this. Let's do a very simple problem on calculating momentum to get a feel for the numbers, okay? Calculate the momentum of a 110 kg football player running at 8 meters per second. So what do you need to do here? Oops, let's go back. What do you need to do here? All you need to do is your momentum is mass times velocity, right? And this is the magnitude that I'm writing. So for mass, you're going to substitute in 110 kg, 110 kgs, and the velocity is 8 meters per second. So it's clearly going to be 880 kg meter per second, right? What about the next case? Part B of this problem, calculate the linear momentum of the Earth as it orbits the sun. So here we see that there's a word preceding momentum, and it's called linear momentum, which is really what we are studying now, momentum in a given direction, right? And later on, when we do rotation, we will look at rotational momentum, okay, angular momentum, it's called. angular momentum. And we will look at the conservation of that. So for now, momentum is interchangeable with linear momentum because we are mostly in this chapter not studying rotational motion. We will come to that in chapters 7 and 8. So calculate the linear momentum of the Earth as it orbits the Sun. Given the Earth's mass is this and its average orbital radius is this. So we do know the mass, meaning mass times velocity. We do not know the velocity. So you might need to work out the velocity from what is given to you, right? What is given is the average orbital radius, which means you're going to consider the orbit of the Earth to be a circle. So here's my Sun, and I'm not very good at drawing freehand, but this is the Earth going round, okay? Let's write this as E. This is the Sun, and this radius, okay, R is given to us. So the velocity with which this moves, we're going to just look at the speed, okay, which is distance covered per unit time. What is the distance if it goes round the Sun once? That's 1 year, right? It takes 1 year to go around the Sun. What's the distance? That's the circumference of this circle. So that's 2 pi r. Yeah? Divided by the time. We just said the time is 1 year, but we need it in units of seconds, right? The velocity needs to be in meters per second. So the r is in meters, so the numerator is going to work out fine. The denominator needs to be in seconds. So 1 year is 365 days. And then you're going to have to multiply days into the number of hours per day, 24. So that gives us time in hours. Go down to minutes by multiplying by 60. Go down to seconds by multiplying by another 60. And now you have the velocity in meters per second. Yeah? And then it's just a question of substituting in the values. So I'm going to let you look at the answer for this. You need to do these problems on your own, okay? It is not enough to just follow me and think that it looks simple, I can do this. You actually need to do this problem on your own. Okay, so let's proceed. And here's the solution that you're going to go through, okay? So now let's look at the connection between force and momentum. Force is the rate of change of momentum. Okay, so delta P over delta T. Remember, delta P is P final minus P initial. It's the change in momentum at 2 different points, okay? So momentum final is M times VF. Momentum initial is M times VI. Here they're just taking M out in common, right? Divided by delta T. So that's the time elapsed. That's going to give you the force which produced that motion, okay? That change in momentum. Okay. So for a change in momentum to happen, a force, an external force must be applied. Okay, the time rate of change of momentum of an object is equal to the net force acting on it. This equation is also true when the force is not constant, but mostly we will consider cases where the force is, its magnitude is constant. Okay, so let's do a problem on this. During 2007 French Open, Venus Williams hit the fastest recorded serve in a premier women's match, reaching a speed of 58 meters per second. What is the average force exerted on the 0.057 tennis ball by her racket, assuming that the ball speed just after impact is 58 meters per second, and that the initial horizontal component of the velocity before impact is negligible, and that the ball remained in contact with the racket for 5 milliseconds. Okay, so we know the mass of the ball, right? We know the time taken for that change in momentum. Let's sketch a little picture. So here's the ball. Oops, sorry, let's go back. Forgetting to do this. So here's the ball, okay? And she's going to hit the ball, Okay, let's say that's the side of her racket with which she hits it, and the ball is going to go, let's say this way, with a velocity of 0.0, sorry, with a velocity, let's raise this, velocity of 58 meters per second, right? So this is going to be the final velocity. Let's write this as VF. What about V initial? Yeah. Assume that the initial horizontal component of velocity before impact is negligible. So she threw, when you serve, you throw the ball probably upwards, and so it has almost no horizontal motion. So we are interested in that horizontal motion. That's our direction for velocity. And that, they say, you can assume to be 0. So what is my change in momentum? My change in momentum is m times v final minus v initial, which is 0, right? And this takes place over what time? Delta t, that's given to you in the problem. 5 milliseconds, so that's 5 times 10 to the minus 3 seconds. And this is equal to the force, right? Force is change in momentum divided by time. We are being asked for the net average force exerted, which is exactly what this is, right? So this is the magnitude of the force. If you calculate this, you have your answer. You can now put in the numbers, and you can see that, and you should do it and compare your results with what I have on the next page. Okay.